Now, while we generally talk about SIMS in the context of unwanted contamination, it is the industry standard method for tracking intentional implants as well. So these would be trace amount of elements that you intentionally implanted onto your wafers, like dopants. So while not contamination, due to the trace concentration needed to be detected we use SIMS extensively for dopant profiling, specifically for mapping depth profile of boron, phosphorus, arsenic implanted into silicon lattice. So process engineers rely on this data to precisely measure junction depth and verify implant doses, comparing the profiles before and after different thermal annealing steps to monitor diffusion. One of the most impressive feats of SIMS in this application is its extreme dynamic range. In a single continuous scan, the detector can track massive peak dopant concentration, for example 10 to the power 20 atoms per cubic centimeter, and flawlessly follow that concentration curve all the way down to trace background level as low as 10 to the power 12 atoms per cubic centimeter without saturating the detector. And in addition to the broad dynamic range, the true power of SIMS is visually realized when we use it to characterize complex interfaces. Looking at the continuous plotting graph on this slide, you can see how SIMS can continuously track elemental concentration as the sputtering crater gets deeper and deeper. This specific interface clearly visualizes exactly where one film ends and another begins. In this example, we can track the precise crossover between aluminum and oxygen while also obtaining quantitative results, which is not possible with other techniques. But more importantly, from a defect perspective, this continuous profiling is how we find trapped impurities, because if a vacuum pump briefly failed during a deposition transition, SIMS will highlight those trace contamination like a spike in carbon or hydrogen that peak exactly at the interface between two specific layers.